Hello, I'm Vidushi Goyal, PhD candidate at CSC New Mish, and welcome to my talk, MyML, User-Driven Machine Learning. Machine learning is present everywhere, like in Face ID, Google Lens, Gmail autofill, so on and so forth. At present, mobile apps offload machine learning computation back to the cloud server. However, offloading to cloud server leads to many problems, like privacy, the need for a reliable internet connection, bulky data transfer leading to longer latencies and transmission latencies. Hence, this option of offloading is not very sustainable. The other solution is to compute locally on the edge device. There are small edge models that can fit on these resource-constrained devices and have smaller execution time, but they have way lower accuracy compared to cloud models that are large but slow. Overall, there is a wide gap between performance and accuracy of mobile ML models and cloud ML models. Resource-constrained edge platforms are not yet suitable for large, energy, compute, and memory-intensive cloud ML models. In this work, we find that the generic ML models that are trained for thousands of categories to cater to a diverse set of users are an overkill for individual users who usually interact with a handful of categories. Like a wildlife photographer will have flora and fauna dataset, whereas a food photographer will have food-related images. So why not build user-specific models that are small, faster, and as well as accurate? So the question is how to build this user-specific model. We have a three-phase process to build user-specific model. The first phase is the learning phase, and as the name suggests, we learn user preferences. Second is the pruning phase, where we prune original model to build user model. And finally, there is inference phase, where we deploy the user model in real time. For the learning phase, we have a tracking mechanism where we track first 50 to 100 inputs for the predicted class from the original model. And then we pick the top frequently appearing categories as user preferences. In pruning phase, we prune the original model for the newly learned user classes to build user-specific model. A quick background in pruning. So pruning is retraining of original model with prune weight set to 0. It has two components, forward pass and backward pass. The first is forward pass, which is computationally similar to the inference pass, but with prune weight set to 0. The difference between the output from forward pass and the ground truth is the error that is used to update model. This error, along with the input activations generated for each layer, are used in backward pass. Backward pass itself has two components. The first is error propagation, in which we calculate error for each layer, and it's a 3D convolution. The next step is weight update, which is used to calculate weight update for each layer, which is a 2D convolution of the stored input activation and layer error computed during error propagation. In this work, we present bottom-up pruning, where we start from the bottom layer and go up to the top layer. Also, what that means is when we are pruning layer n, everything till layer n-1 is frozen and the same as original model. Hence, there is compute sharing between the inference path of the original model that is currently serving user and the forward pass of the pruning path till layer n-1. Only pruned layer n till last layer needs retraining, and that too for leftover non-zero weights, so it's a lightweight process. The pruning granularity is selected based on the underlying compute engine. In the first case, we have a multi-core ARM CPU that acts as compute engine. For the second case, we have a CPU EdgeML accelerator kind of platform, where the EdgeML accelerator is a systolic array-based inference accelerator like an HTPU. When CPU is used as a compute engine, it can control computation at final granularity with SIMD width of 4 slots. This leads to asymmetric pruning, which is higher pruning rate. Whereas HTPU can support computation at coarse granularity. For example, systolic array size is 64 × 64. Therefore, it utilizes symmetric pruning, which has low pruning rates but doesn't need any control mechanism. For asymmetric pruning, channel IDs with least L2 norm values are pruned with no restrictions on what channel IDs to choose. This flexible nature leads to higher pruning rates. However, it needs a bookkeeping mechanism to map unpruned filtered channels to corresponding input channels. For more details, please look at the paper. For symmetric pruning, channel IDs with lowest L2 norm value summed across all the filters are pruned in layer N. So this constraint nature, where the same channel IDs have to be pruned across all the filters, leads to lower pruning rate. However, pruning same channel IDs helps in retaining dense format and doesn't need any finer control mechanism. An additional benefit is that the input channel corresponding to pruned channel ID can be dropped, which in turn leads in the pruning of complete filter in layer N-1. Hence, symmetric pruning transforms the current dense model to another dense model, which can be supported by HTPU. However, the inference accelerators only support int8 or fixed point 8 precision. However, for MyML, we need FP32 precision for training, which has 32-bit in total with 8-bit of exponent. So we repurpose HTPU to support pruning by using block floating point 16 or BFP16 as a floating point precision rather than FP32. In block floating point, each block will have say n elements and each of them will have their own unique sign and minus a bit. But the exponent bits are still 8 bits and are shared by all the elements in the block. So the dot product of two BFP16 block will be dot product of the 8-bit Mantis and sign bit, which can be mapped directly on any int8 precision accelerator, whereas the exponent bits can be simply added on the CPU side. To repurpose HTPU for training, we have added multiple components to CPU side to support the whole training or pruning purpose. So let's zoom into the picture to understand in detail. So first, we have added a FP to BFP converter, which converts FP32 to BFP16, which feeds the systolic array. Next, each column of the HTPU systolic array is basically one BFP block, and we map individual filters to each of them. The output of the HTPU are appended with final exponents by the exponent adder. There is also FP32 normalization block that converts its BFP16 output to FP32 precision for computation across different blocks. Note, all of these extra computational blocks are bypassed for inferences. So now that we have a user-specific model, this marks the end of pruning phase. And the user-specific model is ready to use. And we move into the inference phase where we deploy the new model in real time. We replace the original model with the user-specific model, and we also develop a collaborative edge system. So this collaborative edge system helps in tracking user preferences. It has a tracking unit to observe deviation in user preferences based on output probability of predicted class and an entropy over the output probability distribution. If the number of images outside the user classes are greater than a threshold, it means that the user preferences have changed and we have to bring back the original model to replace user-specific model. This is here a real-time plot for MyML. So once the model is created, it is deployed in inference phase, which is usually very large, and a collaborative edge system is able to cache the change in user preferences because the number of inputs estimated outside user preference user class have crossed the tracker unit threshold. That's when we quickly discard the user model and go back to the learning phase to build new user-specific model. For our evaluation setup, we have inception V3 model and we randomly select 5 categories as user classes. We use TensorFlow to train user-specific model. We extended the Zinpack library for optimized SIMD implementation and ran our experiments on Snapdragon 855, which is the state-of-the-art octa-core mobile CPU. HTPU results are based on a cycle-accurate scale-sim simulator. I will now show the process of building a user-specific model using a bottom-up pruning. We prune a group of 2 to 3 layers at a time, starting from the bottommost layer. You can see we start with layers 7A, 7B, 7C that are the bottom layers of Inception V3 model. You can also see that with each step of pruning process, the error or a loss is reducing. After pruning the first set of layers, we get a model size of 11 MB. Following this bottom-up pruning, we next prune layers 6D, 6E and use the model created in last iteration as the starting model. Using the iterative process of bottom-up pruning, we finally reach the topmost layers 5B, 5C, 5D and start a pruning process again. You can also see that the error or loss becomes almost constant at this point. Validation on final user-specific model gives a final accuracy of 80% with model size of 4.9 MB compared to an original model of 24 MB with 79% accuracy. We show that we can achieve 1.4x speedup compared to user-agnostically pruned CPU baseline and a 2.3x speedup compared to unpruned CPU baseline, while reducing the model size to 5 MB from 23 MB and keeping the accuracy drop within 1%. For HTTP system, we achieve a 2.25x speedup with 2.3x model size reduction and no accuracy drop. In conclusion, we efficiently build small user-specific ML models for these resource-constrained edge devices to give 2.3x speedup and 54% energy efficiency. Thank you, and for questions, drop me an email.